Welcome everybody in the lecture hall who woke up early today. Welcome everybody on Zoom. Welcome everybody watching us from the future. Today, what's on the menu? I will first finish what we started today with the lessons learned from the past, in particular about SQL. And then we'll dive into cloud storage and how to start storing the data. But before we start, I have a few questions for you in the Clicker app. So let's start with this one. I told you about data shapes. Which one of these is not one of these data shapes, fundamental data shapes? Cubes, tables, trees, circles, graphs. I assume you just need time to connect to the page, and then that should be easy if you paid attention last week. No sound here. I think we checked the sound of on Zoom earlier. It was working on our side. So what do we have? Circles, indeed. Cubes, tables, trees, graphs, and the fifth one, vectors, unstructured, right, for LLMs. So yes, indeed, it's the circles that are not a fundamental shape of data. Then I wanted to get a quick impression on your familiarity with relational databases. Of course, those of you who visited information systems for engineers, you would already be familiar with them, but I would still like to know how it distributes overall. All right. So, as expected, there is a bit of a distribution. Some of you reacted with what is this? It's totally okay. You're in the right lecture. There is absolutely no problem with that because it's complementary. And all you'll need to know to do is learn SQL. Yep, so that gives me a good overview. Since I'm at it, I have another one for you to make you think a little bit. You've all experienced, I'm sure, the progress bar that goes all the way to 99% and then remains there forever. So why do you think when you have a progress bar for transferring files from one disk to another, why do you think it's not uniformly going from 0 to 100%? Is it because the files have different sizes? Is it because it doesn't refresh regularly? It's actually happening at a uniform rate, so it's only something that has to do with the user interface? Or is it not true? Maybe you're lucky and the progress bars always go uniformly from 0 to 100 for you. You're very lucky. Or is it because of the CPU? The CPU is that's the processor of the computer where the computations happen. Central processing units. All right. So let's see. Aha, there is almost a tie between the two. And the answer, in the case of transferring files, is in fact, I didn't register it, but it's the size of the files. What happens is that when you have very large files, let's say a few files each 100 megabytes, then the reason for the time that it takes to transfer them is the throughput. It's sending over the bits and the speeds per second, right? How many bits per second get sent for very large files. But now imagine that instead of very large files, you have a lot of very small files. Many small files of just, let's say, 1 kilobyte each, very small. And then you have 1 million of them. And what's going to happen is that what dominates is the latency, is that every time you start with a new file, you need a moment of inertia, a moment of latency. So that's it prepares for the new file. And so that's why even for the same number of bytes, it's faster to write one very large file than it is to write many small files, even of the same size. And one trick that computer scientists might know is if you want to upload a lot of very small files to a server somewhere on another machine, what you should do is zip the files into a single very big zip file, ship over the zip file, then it's bound by the throughput, so the speed at which it is sent. And then on the other side, you unzip it. That is one of the tricks to avoid the latency. And the reason I ask you this question is to make you aware of latency versus throughput, right? Again, I repeat, if you have a very large file, then what dominates is going to be the speed at which the bits are sent. If you have many small files, what dominates is the latency every time you go from one file to another. It's like you notice when you work on the material, if you would work on a course for an hour, it's more efficient than working for 5 minutes for a course and then another course for 5 minutes and then another course for 5 minutes because you have the context switch. That is the same. It's exactly the same as this latency. All right, but now let us go back to our slides. Which are right here. So I left you with the SQL brush-up. So what is SQL? It is part of this picture that I showed you with all these languages out there. And in this lecture, we are not in the software engineering world, right? All these programming languages. We are not in the machine learning world. We are in the database world, right? And we see that we have low-level application programming interfaces like Spark or Pandas. And then we have high-level query languages like SQL and others. And so SQL belongs here. SQL was invented also in the 1970s, shortly after Edgar Code's seeding paper on data independence and the idea of using tables by Don Chamberlain and Raymond Boyce. Raymond Boyce is the same behind the Boyce code normal form, right? The 3.5 normal form. He gave his name to it. And it was created in San Jose in California. The laboratory actually still exists. IBM still has some laboratory there. And the first commercial implementation of Edgar Code's idea was called System R. And the language was called SQL for Structured English Query Language. The goal of SQL was to be easy to use and understandable, even without much computer science skills, right? To make it accessible for everyone. Their first customer was in 1977, so that was 7 years later. Took more time than for LLMs and ChatGPT to get customers. But still, for the time, it's impressive. 7 years later, Pratt & Whitney was the first customer. Another company that was created was Software Development Laboratories, which actually today is known as Oracle. Who heard of Oracle? Right, most of you, right? It's one of the big vendors of databases. The other big two being Microsoft and IBM. All right, so SQL means this, Structured English Query Language. It is a declarative language. Declarative is like when you go to the Mensa and ask for the food you want, for the menu you want, as opposed to cooking, right? Cooking yourself would be an imperative language where you tell the computer what to do. Declarative language means you just say what you want, just like going to the Mensa and picking one of the menus, right? It is also set-based. Set-based just means that a relational table is made of sets of records, and we manipulate tables, entire tables at the same time, right? Which also makes it scale because it can be billions of records at the same time with a single command. However, the people who released this and called it SQL had a trademark lawsuit, which they didn't win. And so that forced them to rename the language to something else. So they renamed it to SQL. But they still continue to say SQL. It's out of habit. I also was in contact with many people who say SQL, and so I also say SQL. It's your choice. You can say SQL, you can say SQL. It's the same thing, right? It's just two ways of pronouncing the same thing. All right, so the benefit of a declarative language is data independence, meaning that you can implement SQL on whichever physical layer you want. We will see, so that, for example, PostgreSQL is one, but we can replace PostgreSQL with something else, like Spark, which we'll do in a few weeks, and we'll still have SQL nicely running on top of it. This is why it is so important to learn SQL. It's everywhere. It's implemented by many different systems. We'll also see that it's a functional language, and we'll learn also the JSONic language, which is also functional. Functional basically means that it's made of expressions that nest, a little bit like you do addition and multiplication in primary school, except that instead of addition and multiplication, we have database operations instead of arithmetics, right? But it's the same idea that you have expressions that nicely nest within each other. So now I'm going to throw at you a few queries. Those of you who visited information systems for engineers, they will already know it. Those of you who are surprised by this or never saw it, do not worry. The TAs prepared an exercise for you, an entire exercise sheet to initiate you to SQL. You can also easily Google for SQL tutorials. It's all over the internet, right? So you will find plenty of places, and it's really, really easy to learn, right? So this is really my assignment for you to make sure that you can write queries. We have Jupyter notebooks inside the Docker, and you can directly write them in the notebooks and see the results, so it's very interactive. This query here selects from persons, persons being the name of the table that you have up there, here, selects everything, so all the columns from persons, and we have a criterion here. We filter with last name equals Crusher. So only this one survives, and the other two disappear, right? So this is what this query does. It's a filtering query, also called a selection. Then we have this query that doesn't filter anything. However, it picks a few columns. First name, birth date in that case. That is a projection, right? I already told you about selection, projection last week, right? So here we pick first name and birth date. We just keep them, and we do not keep the other columns. Then we can do aggregations or grouping. Here, I would like to have statistics by century. I'd like to know how many people there were in every century. So if you look at the table up there, you see that there are 2 people from the 23rd century, Kirk and Spock, and we have 2 people from the 24th century, Crusher and Janeway, and so that's 2 and 2. And this query here, group by century, is going to say that you want to aggregate by century, and then you want to count for every century you want the count. And so this count star is the magical way of doing that, right? So what you group by should always be repeated because you want to see it here, right? Then the other column is count. You can also do sum, mean, max, average, and so on. Now, if you want to have the whole list of the, it's called clauses that you can have in a SQL query, it's select from where, group by, having order by, limit, offset. What makes it easy is that it's always in that order. You cannot change the order of that. Some are optional. You don't need to have all of them, but it needs to be in exactly that order. So if you haven't done so already, learn that by heart, right? Very, very, very important, right? So select from where, group by, having, order by is going to sort, limit, offset. This is going to be a query that looks at the first residence of all the people, for example, in Switzerland. It groups them by city, but only keeping those with at least 100,000 people. And then it sorts by descending population, so the biggest cities first. And limit 10 offset 20 is called pagination. It's basically like in Google, when you get the top 10 results and you click on next, then you get 11 to 20, right? And so limit 10 is only showing 10 of them, and offset 20, that would be page 3 of Google, right? So 21 to 30, that's called pagination, right? So it's very powerful, right? And you can do a few more things like combine multiple tables. Like this is a join between 2 tables, and here you have spaceships and people, and some people are captains on some spaceships, and so you want to bring these 2 tables together to associate every person with every spaceship that they are a captain of, right? And you also have the possibility to include the people that don't have any spaceship and the spaceships that don't have any captain, right? So this is why here we have the Enterprise D. Picard is not here, so it's all null. And here we have Beverly Crusher, who is not a captain, so you don't have a spaceship here. Is there a question? You can read it. I think you could. I think it would work if you try to do the count without actually showing it in the output. That would work. I should indicate at that point that there are dialects of SQL, just like there's Zurich and Barm-Dutch and Basel-Dutch and Walliser-Dutch. It works in the same way with SQL. That means that if you use PostgreSQL or MySQL or Oracle and so on, they might have a few differences, right? So some things might be allowed in one way and not in another one. For example, some of them will force you to have count star and not use the variable that is in the select because they see it or do not see it depending on the system, right? That's a small example. But we only care about PostgreSQL for this course, and you're going to do the exercise with PostgreSQL. All right. And this one here, you're welcome. And this one here is about nesting, where you show that you can put a select from where inside a select from where, just like you can have a table in a table, just like you can have a dream in a dream in a dream, right? So this is the inception way. So you can reuse a table that you obtained from a select from where, put it in the from of another query, and then reuse it, right? So this is why we say that it's a functional language. Then what we saw, don't be scared by that. What we saw in information systems for engineers is that we have all these Greek letters that are the mathematical formalization of selection, projection, and so on. So sigma is for selection, gamma is for grouping, pi is for projection. Just know that there are Greek letters for that, right? But we are not using that framework in this course, right? So just know that it exists, and then when you have a database system, it's going to take your query and translate it behind the scenes to something that looks like this, right? Something else that we have behind the scenes that you don't need to worry about, you can just ask for them, is indices. An index is like what you have at the end of a book, where you have an alphabetical list of words, and then you look your word and it tells you the pages on which the word appears. You already saw that in a book? Yeah, you did, right? We also have that for databases. It's called an index. And so PostgreSQL has them. MongoDB, which we'll study at the end of the semester, also has them. So I'll give you an introduction also to indices. Another piece of information that you need to keep in mind is that the way you use a database system is important. There are people who are going to use a database system and constantly write and update data. That's the case of a shop on the internet, for example, Digitech Galaxus. When people place orders, it constantly modifies the data in order to input the order. We call it OLTP, online transaction processing. It's write intensive. And on the other hand, we have other uses of databases which are read intensive. It means that you don't actually modify any data, you just read it. That's what happens if you download a data set from the internet, put it on your computer, and analyze it for your master's thesis. That would be read intensive, right? So we call it OLAP, also online analytical processing. I'm saying this because that has an impact on the way that you will implement your system. So PostgreSQL is OLTP, and we'll see that Spark, when you use Spark MapReduce, that we'll see in this lecture, it's more on the OLAP side, right? Where we'll just analyze data that already exists. All right. Nobody too scared so far, I hope. Now I'm going to tell you also some nice things that we have in traditional database systems like PostgreSQL. In short, imagine you're a bank and people go to the bankomat and withdraw money. You want to make sure that the account is going to be withdrawn only if and only if they actually get the banknotes, right? That is an example of what we call atomicity, all or nothing. Either you get the banknotes and it's taken from your account, or you don't get the banknotes and it's not taken from your account, right? And so we have these nice features that you get for free from a system like PostgreSQL. It just gives you that. The first one, I'm going through the four, right? ACID, ACID is the way to remember them. It's an Eselsbrücke, right? ACID, ACID. A is for atomicity. It means that when you have a bunch of queries to modify something, either all is applied or nothing at all, right? That's my example with the banknotes. Could be an example also when you book the train, you want the seat to be booked if and only if you pay, for example, right? So either everything or nothing. That's what we call atomicity. Another thing you get is consistency. An example of consistency in a train is that there's not two people who booked the same seat. I was about to say the same for planes, but we know that reality is a bit different. But normally in a plane, you're not supposed to have two people who booked the same seat, right? That's an example of consistency. And what's nice is that in PostgreSQL, you can define your consistency criteria, and it's going to make sure that it's fulfilled at all times when people use the system. That's called consistency. Then we have isolation. Isolation feels like you're the only one. Again, if I take the example of booking some seats in a plane, when you check in and you pick the seats, it feels like you're alone, right? You might not notice, but there's maybe 100 other people who are also doing the same thing, but you're sitting in front of your computer and it doesn't feel like it's interfering in any way, right? And that's what we call isolation. The system is designed in such a way that it makes you feel like you're the only one using the system, right? You don't see any interferences from other people. This is called isolation. You might have different levels of isolation, but this is the I in ACID. And finally, durability means that when you make updates, they don't just disappear. For example, if you booked a seat in the train, you don't want that booking to just disappear into oblivion, right? You want it to stay. You want to make sure that the data is actually kept and persisted, right? So this is called durability. ACID, ACID, these are properties that you get for free from PostgreSQL of all these database systems. And this is one reason not to use Python, but to use these systems if you want to get these sort of things, right? If you want a database, for example, behind a website that you design. All right, so that's so that you know, and of course, it's like everything else, we're gonna drop that. We're gonna get rid of ACID. We are not going to have these guarantees and so on. So I'm telling you a lot of things we have here because we're gonna get rid of them. But yeah, that's it, ACID. So what's going to happen now during the semester? We are going to see data or tables that have a lot of rows, millions, billions, trillions, quadrillions of rows, right? That's much beyond what PostgreSQL can do. You cannot put 1 trillion rows in PostgreSQL. We're going to see tables that have lots of columns. Lots of columns, meaning potentially millions of columns. You cannot do that in PostgreSQL or in such systems. Typically, a traditional system can have maybe 255 columns in the same table, but then they block you. They do not let you go much beyond that, at least the older systems. But in this course, we are going to see tables that have a lot of columns. But as you can imagine, if they have a lot of rows and a lot of columns, it's going to be sparse, meaning that many of the cells are actually going to be empty, right? And the data is just a bit spread all over the place. And finally, we are going to have lots of nesting, tables in tables in tables in tables. We're going to have a lot of that. And in fact, if I show you the menu of what's going to happen in the rest of the semester, it will be about lots of rows, lots of columns, and lots of nesting. Right, so big data, that's why it's called that way. So I'm done scaring you with the summary of information systems for engineers in such a short amount of time. Before I go to the cloud storage and we actually start with the material, is there any questions? Not in the lecture hall. On Zoom, any questions? Do we have any? Also not? Okay. So I'm going to stop the recording here.